Hello friends, and welcome to Ask Study Kida. This is a very new channel dedicated to all those who want to learn technical topics in a very easy way. This very video is going to be a easy one because it is my very first video. So let us start with an easy topic: stress-strain relationship and elastic constants. Before understanding anything else, I must first tell you what is stress and what is strain. So we are going to first study about stress. Stress can simply be denoted by the symbol sigma and is written as force upon area. It is to be kept in mind that this force is an internal force. This force is going to be an internal force. We can understand it this way. If there is a bar over which a force in longitudinal direction has been applied, then there will be an equal resistive force F inside the bar. So we are talking about this F and not this F. We need to differentiate stress from pressure. Pressure, as we all know, is external force upon area over which this external force is acting. Now, we need to understand what is strain. First, we need to classify strain. Strain can be classified in three ways. The very first one is the most common one: longitudinal strain, shear strain, and volumetric strain. Let us now understand what is longitudinal strain. As we have seen the case earlier, if there is a bar of length L over which a force has been applied in longitudinal direction, it is also known as one-dimensional loading. One-dimensional loading. So, on application of this longitudinal force, there will be a slight extension in the length of the bar equal to delta L. Now, longitudinal strain will be equal to the change in length of the bar upon the initial length of the bar. Now, shear strain can be understood with the help of a diagram. Suppose there is a box which is fixed at the base and over which a shear force is applied. It is a shear force. Then there will be a change in the geometry of the box in this way, and we can denote this angle phi as the shear strain. It is to be noted, shear stress and shear strain are only produced when there is a presence of shear force. If this force would have been in this direction, then there would have been no shear strain. Here we have shear strain equal to phi. The final one, the volumetric strain. The volumetric strain can be understood by taking the example of a cubical box. Suppose there is a cubical box which is quite large in its dimension, as I'm drawing it, and is subjected to equal and alike stresses from all the three directions. Then its dimension will be reduced and the box will have a reduced volume. This, suppose, has a volume V1 and this has a lower volume V2. We can represent volumetric strain as change in volume, that is V1 minus V2 upon the initial volume. So it can also be written as delta volume upon initial volume. Now, as we have already understood what is strain and what is stress, now we can easily understand the four elastic constants that are most widely used in strength of material and other subjects dealing with material properties. So let us discuss the elastic constants. Elastic constants. Based upon the stress and strain characteristics, there are four elastic constants, namely the modulus of elasticity, that is represented by E, the bulk modulus represented by K, the modulus of rigidity represented by G, and the final one is the Poisson's ratio. Here it is very important to tell that if a material is isotropic, then out of these four elastic constants, there are two constants which are independent and can be found, that is E and mu. Using these E and mu, we can find out K, and G. So for isotropic material, there are two constants. For orthotropic material, there are 9 independent elastic constants, and for anisotropic material, there are 21 independent elastic constants. Now let us understand each elastic constant in a detailed manner. The first one is the modulus of elasticity, and it is the most commonly used elastic constant, that is E. As we all know, the modulus of elasticity E was derived by Robert Hooke's, so it is also known as Hooke's constant. Now by Hooke's law, we already know during one-dimensional loading, the stress will always be proportional to strain. We have denoted strain by epsilon. In order to remove this sign of proportionality, we need to add one constant which is known as E, or the modulus of elasticity. So in turn we can write the modulus of elasticity is the ratio of stress to strain in one dimension, or in longitudinal loading. The second one is The second one is the bulk modulus, which is denoted by K. We have already studied about the volumetric strain. So, and we have, while studying about the volumetric strain, we have seen that the cubical box was acted upon by the alike stresses in all the three directions, and that was sigma. To recall it again, I'm drawing the figure again. So, if this is acted upon by sigma from all the three directions, then and the shape is reduced, or rather the volume is reduced and becomes V2 from V1, then volumetric strain will be V1 minus V2 upon V1, and bulk modulus will be defined as volumetric stress upon volumetric strain. So we have till now studied two elastic constants. The third one is the rigidity modulus. This rigidity modulus is mostly used while we are dealing with the torsion problems and can be defined as shear strain, shear stress, it can be defined as shear stress upon shear strain. Now we can understand the shear strain with respect to torsion too. Suppose there is a bar, a circular bar subjected to torsion, then while a torsion T is applied on this circular bar, this radii will tend to come to this position and thereby giving a shear strain. So this is shear strain, and shear stress will be produced due to the torsion T. The final one is the Poisson's ratio. So Poisson's ratio is one of the very important elastic constants and is used for derivation of K and G from E and mu. Or we can say mu is used to relate all the three A, K and G. So now to understand Poisson's ratio, we need to take a case of one-dimensional loading again. Suppose this is a circular bar which has been subjected to unidirectional or one-dimensional loading with F. The shape of the bar is changed as the force F is applied. The bar which had initial diameter D1 will now be reduced to D2, and the length of the bar will also increase by delta L. Now here, to understand the Poisson's ratio, we need to understand the lateral strain. The lateral strain will be, we have already understood the longitudinal strain. So longitudinal strain is in this direction. This direction will give us longitudinal strain, and this direction will give us transverse strain or lateral strain. So to calculate lateral strain, we need to apply the similar approach as the longitudinal strain. In lateral direction, there is a change in diameter from D1 to D2, and the initial diameter was D1. So it is the lateral strain. And longitudinal strain we have already discussed. Longitudinal strain will be delta L upon initial length L. Now Poisson's ratio. Poisson's ratio is defined as the lateral strain upon longitudinal strain. If you are following a sign convention, we can also use a minus sign here. If you take the lateral strain in negative, if you take the lateral strain with a negative sign, then we can use a negative sign here in the formula for Poisson's ratio too. So now we can write down the final relation for the Poisson's ratio, that is E epsilon lateral upon epsilon L. Now I need to make this one thing very clear. Some of the books would be using mu is equal to minus lateral strain upon longitudinal strain. This relation is also very correct because we are seeing in the diagram we are applying a tensile force and the diameter of the bar is reducing. So we can also take epsilon lateral with a negative sign. So while taking epsilon lateral with a negative sign, we can write down the relation longitudinal. So it will give us the same relation as we had obtained earlier. So these are the 4 elastic constants that we have discussed. I hope you have understood the stress-strain relationship in a better way, and you have also understood the 4 elastic constants and their relation between all of these. I would be discussing further more topics in coming videos. So please like this video and subscribe to my channel, as this is my first video. So I'm sorry for all I think you have enjoyed the video, so please subscribe. Thank you.